Welcome back to the deep dive. If you've been following the AI space for, I don't know, even just the last year, you've seen this massive shift happen.
Oh, absolutely. It's been incredible to watch.
Large language models, or LLMs, they're not just these clever text predictors anymore. They've really matured into true digital assistants.
Exactly. They're agents now. They can perform these complex, multi-step operations and actually do things in the real world.
And that's the key, right? The doing part.
That's the entire game changer. We've moved out of this realm of pure text generation and squarely into application development. I mean, these agents are interacting with databases, they're navigating file systems,
Generating complex reports.
generating complex reports based on multiple data sources, even executing custom code. But this maturation, as exciting as it is, has introduced, a massive headache.
Complexity and chaos.
Complexity and chaos in integration. That's the perfect way to put it.
I can just imagine. Because if the power of the LLM is now bottlenecked by how reliably it can talk to the external world, whether that's a CRM, an email client, a financial database,
Right.
you just need consistency. If every single developer or company builds their own bespoke system for how the AI opens a spreadsheet or calls some third-party API, you just end up with
Absolute fragmentation.
and a huge pile of unmanageable technical debt.
That is precisely the challenge facing the industry right now. It's that moment when a technology shifts from being a sort of research curiosity to an industrial utility.
And whenever that happens.
Whenever a technology hits that point, the market just cries out for standardization. We need standards for how AI models interface with the world to ensure interoperability and, I think most importantly, efficiency. Efficiency in integration and workflow repeatability.
So today, our mission is to cut through that alphabet soup of standards and really dive into what many people are seeing as the essential framework for the next generation of agents.
Agent skills.
Agent skills. This open-source packaging format introduced by Anthropic that formalizes how we define these complex agent behaviors. So we're going to cover the specific advanced problem this standard solves.
And how it stacks up against what's already out there.
Exactly. How it compares not just to existing tool standards like function calling, but also to newer protocols like MCP, and how it enables the creation of these highly sophisticated, reusable workflows.
So if you want to understand the architecture required to build truly reliable AI agents, this is the deep dive for you.
Okay, let's unpack this, and I think we have to start where this whole revolution really began, function calling. For a lot of developers, I think this was the moment the LLM became, truly functional.
It really was.
So can you define function calling and specifically, what was that crucial problem it solved?
Absolutely. Function calling is what I like to call the action blueprint. It's a standardized model interface pattern. OpenAI pioneered it most visibly with GPT-4 and its variants, but other models quickly adopted similar approaches.
And before this, what was the world like?
Oh, it was a mess. Before this existed, if a user said, "Send an email to Jane," the LLM would just output text, something like, "I should send an email to Jane."
Okay.
So then the developer on their end had to write this complex, often really fragile parsing code. We're talking regular expressions, custom NLP, all just to figure out the user's intent and try to extract a function name and the arguments.
That sounds like a recipe for constant failure,
Mm.
especially if the model just decided to be a little creative with its wording one day.
It was incredibly brittle. Absolutely. Function calling changed everything because it added structure directly into the model's output.
Okay, so no more guessing.
No more guessing. Instead of free text, the LLM emits a structured tool call. It's basically a little snippet of JSON that specifies a function name and its required arguments.
So it's standardized how the model asks for an action.
Precisely. The developer defines the function signature in the prompt, the model sees that definition, and then its output, if it decides to act, is guaranteed to be a machine-readable JSON object. Something like, function, get weather, arguments, location, Paris.
That is a fundamental leap forward. It moves the LLM from just suggesting an action to precisely requesting an action that the application can execute without any ambiguity.
Right. The application running the LLM, what we call the agent harness, just reads the JSON, executes the tool against the external API, and then feeds the result back to the model for the final response.
So it standardized the intent.
It standardized the intent. But, and this is a big but, here is where the deeper engineering problems started to emerge. Even with function calling, two major operational issues persisted.
And the weight of solving them.
Fell squarely on the client developer, which is, often you, the person building the application.
Okay, so we solved the model's output problem. What was this persistent client-side integration pain?
Well, the first issue was provider inconsistency. While function calling standardized the concept of a tool call, the definitions themselves,
Hmm.
they weren't directly portable.
Meaning?
Meaning every LLM provider, OpenAI, Anthropic, Google, you name it, they all handled the tool signature differently in their API calls. So if you built a whole custom tool ecosystem for one vendor,
You couldn't just drop it into another one.
you couldn't just drop that same schema into another vendor's system and expect it to parse and function identically. It was a nightmare.
Right. So even though the tool was the same, say a function to search a database, the way you had to define that function schema, the JSON structure, the names for the arguments,
Yeah.
all of that required tailoring to the specific API and the model's particular training.
It locked you in. It locked you into a specific vendor's format.
That sounds like massive maintenance overhead for anyone trying to build like a multi-model agent system.
It was. And the second, and I would argue even more crippling issue, was the execution burden. Function calling only tells the model what to ask for. It doesn't handle any of the actual orchestration.
You mean the wiring up, the plumbing?
Exactly. The plumbing, the actual execution, the error handling, result formatting, the sequencing of tool calls, that was all handled completely outside the model environment.
So you had to build all that yourself.
I remember wrestling with this exact problem a couple of years ago. You had to write custom client code just to parse the JSON request, then figure out which microservice endpoint to hit, manage API keys.
And what if the data comes back in a weird format?
Exactly. It might be at XML or CSV, so you have to format that result into a concise string that fits back into the LLM's context window, then manage retries or failures. You had to do this bespoke implementation for every single application. It was just relentless integration work.
So, long story short, function calling was a great protocol for the LLM to speak, but it left the application developer drowning in the mechanics of execution and cross-platform compatibility.
Yes. It standardized the request, but left the ecosystem highly fragmented on the execution side.
And that functional gap, that execution burden, I'm guessing that's what led to the next step.
That is exactly what led Anthropic to introduce the Model Context Protocol, or MCP. They saw that these sophisticated agents needed a standardized execution layer that was entirely model agnostic.
Okay, wait, let me make sure I understand the layering here. If function calling was the blueprint for the model's output request, how did MCP situate itself? Was it like trying to replace function calling?
Not at all. That's a great question, and it's a common point of confusion. MCP is a standard client-server protocol that sits above function calling.
Okay.
It's specifically designed to address that execution gap we were talking about. Function calling remains critical because, well, that's the language the model speaks. MCP standardizes the infrastructure that listens to that language and handles all the complexity that comes after.
So it's a service layer for tool execution.
Think of it as a standardized service layer for tool execution that manages the connection to many tools in a consistent way.
So if I'm the client developer, instead of me writing a custom handler for 50 different external APIs, I just speak the MCP language to an MCP server, and that server just handles all the integration messiness.
That's spot on. The MCP server defines the tool schema and manages the execution logic according to the standard. And this means a tool definition becomes truly interoperable.
And what makes it interoperable in the MCP standard? How does it do that?
It defines a standardized way for the server to describe and expose the tool. So this includes canonical formats for inputs, outputs, status messages, all independent of the model's native function calling format.
I see.
It standardizes the whole life cycle of a tool call: registration, invocation, and status reporting. So what this means is whether you're routing a call to a Python script or a REST API or some internal microservice, the result that comes back to your agent harness is always in the predictable MCP format. It cleans up the entire execution layer.
That makes perfect sense. So the model knows how to ask. It's function calling. And the execution server knows how to route and run that call consistently, which is MCP. This sounds like we've solved most of the problems you mentioned.
It solved a huge chunk of them.
So what complex, multi-step task was still left open that required this third standard, agent skills? What was the remaining gap?
The gap that remained was the effective handling of reusable, complex workflows and procedural knowledge.
Workflows.
MCP and function calling are designed for single-step transactional tool use, for example. Retrieve user ID 45 or check the stock price. These are discrete
A
transactions.
single action.
Yes, a single action. But what if the user's task is far more abstract, like audit this repository for security vulnerabilities and generate a remediation plan?
Or the example you used before, generate the quarterly financial report.
Exactly. That's not one action. That's, I don't know, a minimum of 15 steps. You have to query 3 different databases, clean the data based on known anomalies, run an analysis script that's housed in a specific directory.
Integrate those results into a specific template, verify stakeholder data against some external reference document, and then write the final summary.
You've got it. That's not just a collection of functions. That's a sophisticated institutional methodology that needs to be followed precisely every single time.
It's a recipe.
It's a multi-step recipe that requires detailed, token-efficient instructions, supporting scripts, and template assets. And neither function calling nor MCP was designed to package, deploy, or, and this is the key phrase, progressively disclose that kind of reusable, complex procedural expertise to the model in an efficient way.
They deal with the mechanics of execution.
But not the architecture of the knowledge required to perform the task reliably. And that's the void Agent Skills was created to fill.
This is the moment Agent Skills enters the scene. Okay, so if function calling gives us the single instruction and MCP provides the execution service, the agent skill is the full methodology. It's the recipe itself.
That's the perfect analogy.
So how would you technically define agent skills?
Technical definition first. Agent Skills is an open-source packaging format for reusable agent capabilities. And it encompasses not just function signatures, but complete instructions, complex workflows, and optional supporting assets like scripts, templates, and domain-specific documentation.
So let's take your code auditor example. If I'm building a code auditor agent, the function call might be read file, right?
Right.
MCP would ensure that read file call executes smoothly against the file system.
Yep.
But the skill is the full 30-step methodology that tells the agent. To conduct an audit, first you read dependencies.txt, then you run script securitycheck.py, and if that script returns error code 404, you need to consult the best practices stored in references vulnerabilityguide.md.
That is the perfect distinction. The core benefit is standardizing how that entire body of procedural expertise is organized, packaged, and injected. And this lets us guide the model's behavior across tasks with really high consistency. And the secret sauce to making this all work efficiently is progressive disclosure.
Progressive disclosure. Okay, let's really hammer that home because token cost is always paramount when you're dealing with LLMs. We need to know how the agent runtime achieves this efficiency.
Okay, think of the model's context window like a computer's RAM. It's extremely fast, but it's highly limited and very, very expensive.
Right.
The model needs its RAM to store the user's immediate query and its current thinking process. Now, if you just dump a 500-line, 5,000-token instruction manual, which is the full-skill workflow into the RAM for every single query...
You'd slow everything down and your costs would just skyrocket.
Exactly, even if that skill isn't even needed for that particular query.
So the full knowledge base, the skill that's like the hard drive or external storage, it's persistent, it's huge, and it's cheap, but it's slow to access.
Precisely. Agent Skills leverages this exact distinction. The rule for designing a skill states that the metadata, a very concise description of the skill and when to use it, must be kept extremely small.
Yeah.
The ideal is 100 tokens or less.
And that tiny metadata payload is the only thing that's always loaded.
It's the only thing that is always loaded into the model's active context for discovery. It's always in the RAM, so to speak.
So every time I chat with the agent, it only sees this tiny list of skill names and brief descriptions, effectively saying, hey, I know how to process invoices, I know how to audit code, and I know how to generate reports.
Yes. The agent knows the existence of the recipes, but not the recipes themselves. Then and only then, when the user's task matches that brief description like, can you audit the code, the agent runtime identifies the need.
And only then does it take the hit.
Only then does it take the hit, pause, and load the full, detailed 500-line skill.md file into the model's working context into its RAM. This is progressive disclosure. You only load context when it's absolutely necessary, which makes these complex workflows token efficient.
Agent Skills is clearly an evolution, though, right? It's not some sudden invention. It feels like it's been heavily influenced by the previous generation of agent development.
Oh, absolutely. The entire format is built on insights that were gleaned from the rise of file system-based agents.
So systems like Claude Code or some of the early versions of OpenAI's Codex projects.
Exactly. These were agent architectures that allowed foundation models to operate within a sort of terminal-like environment, interacting with code and files through a simulated command line interface, a CLI.
So the model wasn't just talking about code. It was actually writing, executing, and then reacting to general code output, almost like a human developer working in a terminal.
Yes, and this revealed two, I think, profound architectural truths about agent design. The first one is that executable code actions elicit better LLM agents.
What do you mean by that?
Well, developers realize that if you give the LLM highly specific, predefined functions like rename file or find text in file or add three-line softcode, you're really constraining its flexibility. It can only handle the scenarios you've already anticipated.
And the alternative is what?
The alternative is providing highly general tools, like just give it the ability to write and execute general shell commands, bash, Python, sed, grep.
Ah, I see.
The model's inherent strength lies in its ability to generate and comprehend generalized code. By letting it compose a robust MV, old name, new name bash command, or a sophisticated multi-line Python script that imports libraries, you're relying on the model's intelligence rather than the rigidity of your predefined tool library.
More general tools lead to infinitely more flexible agents.
That's it. That distinction is so incredibly important. Instead of a developer having to maintain this massive library of brittle, specialized functions, you just rely on the LM's own training to compose the necessary action using a small set of robust general-purpose tools.
That makes a ton of sense. And what was the second finding?
The second finding relates directly to that token cost issue we were just discussing, the file system as memory. These agents were equipped with standard CLI file handling commands, lascat, grep, touch, mkofl it.
All right.
This meant they could actively manage their own persistent memory using literal documents and directory structures.
So going back to our RAM and hard drive analogy, instead of trying to stuff every past interaction or every artifact into the model's working context into RAM,
It just saves it to a file.
the agent just saves a detailed log or a draft report or a summary document to a file on the simulated hard drive and says, see draft report dv2.md.
Exactly. It uses the file system to offload all that unnecessary information. It can reference past artifacts without needing the full content in the working context, which, respects the token limits. The file system acts as persistent external memory, much like a human relies on documentation and a well-organized project folder.
Okay, wait, let me just introduce some friction here because this sounds a little scary. If we are empowering LLMs to write and execute general bash commands, aren't we introducing huge security vulnerabilities?
A critical question.
When we allow what you call high-freedom code execution, how does the agent skills standard address or mitigate the inherent dangers of running code that's generated by an AI?
That is a critical question, and it's why it's so important to remember that agent skills is a packaging format. It relies on the supporting agent harness to enforce the security boundary.
Okay, so the skill defines what to do.
The skill itself defines what the agent should do, and sometimes it even provides the exact script it must run. The execution environment, however, has to be sandboxed.
Right.
The key is that the agent's skill standard encourages the designer to define the appropriate degree of freedom. For high security, fragile operations like, say, connecting to a sensitive server, the skill designer must use low freedom.
Meaning they pre-write a safe script.
They pre-write a safe, parameterized script, store it in the scripts folder, and the agent must call that script without modification. But for general file manipulation that runs in a contained, isolated environment, they can use high freedom and let the agent compose the bash command.
So the standard dictates the structure, but the developer has to apply the security discipline.
Yes. Through sandboxing and constrained execution where necessary, the engineering discipline required is really evident. You have to document not just the steps, but the appropriate safety level for each step.
And that ties into the third building block you mentioned.
It does. Agent S.MD developers building these early file system agents realized something really effective. Since the agents were trained on public code bases, which are full of remaze and contribution guidelines, providing repository-specific guidance in a top-level markdown file worked incredibly well.
Ah, yes, the agent S.MD practice. It's basically documentation written for the AI.
That's a great way to put it. It's precise, agent-focused guidance that helps the system quickly understand a repository's rules or its structure.
And agent skills formalizes this.
Agent skills formalizes this. It takes that concept of packaging documentation, tools, examples, and all the supporting materials into a portable, structured unit of functionality, a behavior. It's the standardized wrapper around all the successful best practices we've learned from building these complex CLI-based agents.
Okay. We've built up this architecture, layer by layer. Function calling, MCP, and now agent skills. For anyone listening right now, these overlapping concepts can be really confusing.
They can be, yeah.
So let's just take a breath and use the data from the standard definitions to clearly delineate the distinct role and the layer of each standard.
This clarity is absolutely essential for anyone trying to architect a modern agent system. And the key thing to remember is they are not competing standards. They are complementary layers in the same stack, and each one is solving a very specific problem.
Okay, so let's start at the bottom. Function calling. Where does it sit?
Function calling operates at the fundamental model API level. Its primary job is to be the interface layer for single tool use.
Okay.
It defines the required signature, the name, and parameters that ensures the model can precisely request one action at a time. That results in that structured JSON output we talked about. It's purely focused on the communication protocol between the model and the application layer.
So it's the standardized request language. All right, next up, the Model Context Protocol, MCP. Where's that in the stack?
This sits higher at the agent orchestration layer. Its primary role is the orchestration integration layer. It is the unified server that routes the model's request to the correct service, regardless of whether that service is some legacy API or a modern microservice.
It standardizes the execution and result return across all these different platforms.
That's it. It abstracts away the specific API protocols, ensuring the tool request is run consistently and the output is returned uniformly. It just cleans up the messiness of external systems.
Okay, makes sense. So that brings us to the top layer, agent skills.
Correct. And agent skills operates at the highest level, the knowledge context layer. Its primary role is the knowledge and workflow layer.
So it's not about the execution mechanics.
Not at all. It's about providing the high-level, reusable, step-by-step methodology and the domain knowledge necessary for the model to handle complex, multi-step tasks consistently and efficiently. It's focused on how to organize the procedure.
I find the comparison of function calling being the single request, MCP being the execution system, and agent skills being the detailed, complex recipe to be incredibly helpful here. It really clarifies the roles.
It's a great way to think about it.
But the mechanics of activation,
Yeah.
that's maybe the most confusing point for someone coming from a traditional function calling background. How does the agent decide to use a function call versus activating an agent skill? They both sound like the model is choosing what to do next.
The mechanism of activation is defined entirely by progressive disclosure, and it really highlights the different layers of awareness the agent possesses. It's a great question.
So a function call, how is that triggered?
Function call is triggered dynamically by the model during generation. The model has the function description loaded right there in its context in its RAM, and when it determines that a query requires that action, say book a flight, it just stops generating prose and outputs the structured function call intent.
So it's an interrupt in the flow of text generation, a real-time decision.
Exactly. It's reactive.
Okay, and MCP's role in that.
MCP's role is that it supports this function call. So the model generates the function intent, the client recognizes it's an MCP managed tool, and then the client takes over to execute the call via the MCP server. MCP standardizes the execution process that's triggered by the model's output.
Got it. Now, agent skills. How is that different? It sounds less reactive.
It is. It's much more strategic. Remember that the skills metadata, that tiny 100 token description, is preemptively loaded in the prompt for discovery.
Right.
So this makes the model aware that a methodology exists for a complex task, but it doesn't have the full instructions yet.
So the model just knows the names of all the available recipes up front.
Exactly. And when the user asks for a task that matches a skill's brief description, say, analyze the Q3 market data, the model decides to activate the market analysis skill. This is an internal decision by the agent runtime. It's saying, I have a method for this.
And at that point, the agent harness pauses and loads the full instructions.
It pauses the main task and loads the entire contents of the skill.md file into the model's working context, into its RAM.
And that full detailed instruction set then becomes the primary guidance for the model to follow for the rest of that task.
Correct. The agent then follows the multi-step guidance laid out in the skill. And here's the synthesis. This is where it all comes together. That guidance itself may then instruct the model to perform low-level transactional actions,
Which it executes using function calls.
And those function calls are likely managed and routed efficiently by an MCP server.
So they are not alternatives at all. They are layers of control. Agent skills controls the what and the how, while function calling and MCP manage the underlying transactional execution.
That's it.
You really need all three layers to build the most sophisticated, large-scale agents that can handle complex, recurring workflows reliably.
They perfectly complement each other. Function calling structures the communication, MCP standardizes the execution service, and agent skills standardizes the reusable workflow and the knowledge structure.
Let's shift focus now to the architectural discipline required to actually implement this standard. For developers who are interested in creating these reusable workflows, what does this packaging format actually look like, and what are the rules for designing the skill itself?
The structure is intentionally simple, which I love. It leverages that successful file system heritage we discussed. An agent skill is essentially just a specialized directory structure.
Okay, so a folder.
A folder, typically named descriptively, like analysis and reporting.
And what are the absolute must-have files inside that folder? What's the bare minimum?
The required components are just the directory folder itself and the primary markdown file, skill.md. The folder name and the skill name must match, just for clarity.
But the real utility comes from the optional stuff, right?
The utility of the skill often comes from the optional structured subdirectories that support the complexity. There are three main ones you'll see. First, scripts. This is critical. It holds executable CodePython, Bash, maybe some specialized binaries, that supports the core workflow. These scripts manage operations that are too complex, too fragile, or, too security sensitive for the LLM to write on the fly.
Got it. What's next?
References. This is for additional dense documentation, often domain-specific knowledge that would just clutter up the main workflow. Think of things like compliance documents, specific API parameter dictionaries, or institutional style guides.
And the third?
Assets. This is for static resources. Things like report templates, HTML, LaTeX configuration files, diagrams, or large JSON schemas.
It's a beautifully intuitive way to package complexity. The skill.md is the entryway, and everything else is just compartmentalized supporting material.
And it's only loaded into the context window if the model's activated workflow actually requires it.
Okay, let's focus on the centerpiece, the skill.md. How is this file structured, and why is it so important that the front matter be so concise?
The skill.md is strictly divided into two essential sections, the front matter and the body. The front matter is the metadata. It's typically formatted using YAML and delineated by those triple dashes.
And this is the part the client parses before activation.
Exactly, to surface key information to the LLM for discovery.
So what's required in that metadata?
Mandatory items include the name of the skill and, critically, a concise description. This description is the sole piece of text the LLM uses to judge when to activate the skill. You might also include things like license, version, and author.
And this leads us right back to our token efficiency rule. You said the metadata has to be kept to 100 tokens or less. That's incredibly tight.
It is.
How does that constraint force developers to prioritize when to use the skill versus what the skill actually does?
It demands surgical precision in describing the skill's trigger. You must describe the purpose or the trigger condition, not the 50 steps it takes to execute it.
Can you give me an example of a good versus a bad description?
Sure. A good description might be, generates quarterly financial summaries and runs compliance checks. A bad description would be, reads data from SQL, then calls Python script 1, formats results, then calls Python script 2, then checks the database, etc., etc.
I see. And because that metadata is always loaded for every single interaction?
Keeping it short ensures token efficiency across the board. I mean, if the metadata for 50 skills totaled 10,000 tokens, you'd waste thousands of dollars in compute time on queries that just ask, tell me a joke.
So by keeping it minimal, we ensure the agent is lightweight until the moment it needs to execute a complex workflow.
Right. And the body, conversely, contains the full, exhaustive, step-by-step instructions that are loaded only once the skill is activated.
Okay, so now we shift from the plumbing, the file structure, to the architecture, the thinking. Creating a skill isn't just about dumping files in a folder.
Not at all. It's about ruthlessly engineering the workflow for an AI, much like a chef writes a recipe that's designed to be repeatable by anyone.
So what are the key best practices that differentiate a reliable, repeatable agent skill from just, a very long prompt?
First and foremost is absolute conciseness and efficiency. You have to challenge every single piece of information. Assume the model is highly capable of common sense reasoning. Only give it instructions it really needs.
And there's a recommended length.
The standard recommendation is to keep the primary skill.md under 500 lines. If you have more detail, split it. Put it into separate files in the references directory, and then instruct the LM on when to read those files.
Okay, what's next?
Next is instructional clarity. And this involves subtle but really powerful conventions that aid LLM interpretation.
Like what?
For one, use gerund form naming for the skill directory and name. Processing PDFs, analyzing spreadsheets. This clearly defines the behavior or the action being performed rather than just a static object name.
Okay, that hits.
Also, write in the third person. This is a subtle but powerful nuance. You should write, processes Excel files according to corporate compliance guidelines, not, you can use this to process Excel files.
Oh, that's fascinating. Why is that?
Writing in the third person reinforces the skill's description as an objective, factual capability, which LLMs respond really well to. It's not an instruction directed at the agent itself. It treats the skill as objective knowledge that the agent is accessing, not a command being issued to it.
I see. That's a neat trick.
It is. And we also heavily rely on conditional workflows. Since the LLM is driving the process, you have to basically embed a flowchart inside the instructions.
So you provide checklists.
Provide checklists that the model can explicitly copy and check off as it progresses. For every major decision point, use clear structures. If the data is deemed sensitive, follow procedure A. Otherwise, proceed directly to path B. This reduces the ambiguity that leads to agent hallucination or looping.
That seems to be the core challenge, right? Enforcing reliable, deterministic behavior in a system that's built for creativity.
It is. And that leads to the final point, technical robustness. This requires setting the appropriate degrees of freedom we discussed earlier. For fragile or highly critical operations, you must use low freedom.
Meaning, provide explicit scripts.
Provide explicit scripts in the scripts directory that the agent is instructed to execute without modification, like a script that sanitizes database inputs. But for open-ended tasks, like summarizing a document, you can allow high freedom using generalized text instructions.
And what about portability?
Because these skills are designed to be portable across different agent harnesses and systems, technical requirements have to be universal. Always use relative paths, no absolute paths. And crucially, always use /script-analyze.sho and strictly avoid backslashes, which are common in Windows paths, to ensure cross-platform compatibility.
You also have to list your dependencies.
Oh, yes. The documentation must explicitly list any required package dependencies so the execution environment knows what needs to be installed.
This just highlights that building a successful agent skill isn't just about writing a good prompt. It's about applying meticulous workflow engineering discipline to document every process better than we ever have before.
It really shifts the entire focus, from prompt engineering to genuine software architecture and procedural documentation.
Theory is great, but let's see the payoff. We have a detailed reference here about a skill that was created to interact directly with the Apple Notes application. This feels like a great, relatable, real-world example of BioS Bring Your Own Skill.
It's a perfect microcosm of what skills are meant to achieve. The goal was to allow an agent to perform CRF, create, read, update, delete operations directly on the user's Apple Notes application.
Why? Why Apple Notes?
Because notes are a persistent storage location that's familiar to the human user. The agent needs a persistent place to log tasks, to store its findings across sessions, and save data where the user can easily see it later.
So the agent is saving its thoughts and its outputs into a location that acts as a kind of external shared memory between the AI and the user.
Exactly. And the mechanism is complex because Apple Notes doesn't offer a simple REST API. So the skill uses a lightweight script, something like create-note.py, that wraps underlying system commands, specifically AppleScript, to execute the action.
And it's sandboxed, presumably.
For safety and organization, yeah. All notes created by the agent are scoped to an automatically created agent notes folder.
Now, this gets to the core of why agent skills is needed over just a simple function call. The tool execution itself is simple. You just run a script. But what crucial, ultra-specific procedural instructions does the skill.md body provide to guide the LLM's output formatting?
This is the most crucial takeaway for the listener. The skill.md doesn't just say call create-note.py. It provides explicit usage instructions, command line examples, and a detailed HTML reference table, complete with supported tags and their usage.
Wait, why the obsession with HTML formatting? That seems oddly specific.
Because the underlying AppleScript interaction dictates that the note content must be supplied as HTML for rich text. If the LLM just outputs markdown or plain text, the note will look terrible, or it'll fail to render tables, lists, and formatting that are crucial for a professional summary.
Ah, I see.
The skill has to dictate that the LLM, when composing its output, must use specific HTML tags. For instance, the skill.md body instructs the model that 1. The title argument is automatically formatted as an H1 header, so the model should keep the title brief.
Okay.
2. Div must be used for paragraphs. 3, T must be used for monospace text, like code snippets or file paths. And 4, and this is a great example, if the LLM needs to display a table of data, it has to use the specific detailed HTML structure of Objectable to ensure the Apple Notes rendering engine will accept it.
Wow. So the procedural documentation is forcing the LLM to think like a formatter, specifically constrained by the underlying tool it's using.
That's it.
The LLM is essentially saying, I see the task, I've loaded the skill, and now I know that to execute this task successfully, I have to produce text structured exactly like this obscure HTML format.
That is precisely the mental shift Agent Skills enables. It elevates the LLM from a generator of general intent to a meticulous executor of domain-specific constrained procedures. It demonstrates that the constraint is often not the LLM's intelligence, but the friction of the real-world tool it is being forced to interact with.
That also leads us straight into the limitations then, because even with perfect documentation, the skill cannot overcome the functional limits of the specific tool it is wrapping.
That's exactly right.
What did this Apple Notes example highlight regarding those real-world constraints?
It exposed several inherent constraints of trying to automate system-level tools, and the documentation for this skill explicitly lists these issues, which I think is great, honest practice.
So what were some of them?
For instance, checkbox state is inaccessible. While Apple Notes supports interactive checklists, the underlying AppleScript interface only allows the skill framework to read them back to the LLM as regular static bullet lists.
So the LLM can't programmatically check or uncheck a box.
It can't. Second, links are stripped on save. This is due to limitations in the underlying AppleScript interaction. If the LLM tries to include a hyperlink, it'll just fail.
So the skill standardizes the workflow structure, but it absolutely cannot fix underlying API limitations. The documentation has to be brutally honest about what the agent cannot do reliably, even if the instructions are perfect.
Exactly. And a third one, while it's technically possible, adding images and attachments programmatically is highly impractical for LLM agents.
Why is that?
It would require the agent to manage these massive base64 encodings and large resources, which just blows up the token context and violates the efficiency goals of the skill. These limitations have to be clearly communicated to prevent the agent from attempting tasks that will reliably fail.
It's clear why this standardized framework is necessary for internal bespoke tools, but is this format seeing broader adoption beyond just, internal Anthropic use?
Absolutely. The fact that Agent Skills is an open source standard has driven some really impressive adoption in complex domains. It proves that workflow standardization is a generalized industry need.
And what's a good example of a complex, domain-specific application that's using this framework?
You should look at the Hugging Face HSLM trainer skill. This is just a powerhouse example of leveraging agent skills for highly technical automation. Hugging Face encapsulated their entire LLM training, monitoring, and validation ecosystem into a complete skill package.
That is a massive amount of complexity. I mean, training large models involves dozens of highly specific sequential steps, parameter checks, validation runs.
Precisely. And this skill allows a compliant agent, like a CLI agent, to perform actions like hyperparameter validation, monitoring of training runs, and the actual training initiation on Hugging Face services.
And it does this all just guided by the skills markdown files.
Crucially, yes. It does this entirely guided by the structure and procedural expertise contained in the skills markdown files. And what this means is Hugging Face didn't need to hard code this logic into every agent that might use their service. They just provided the reusable, portable expertise package.
That truly demonstrates the power of compartmentalization. Instead of developers trying to embed complex machine learning workflows inside some general agent, Hugging Face just provides this specialized domain expertise.
And any compliant agent can immediately adopt that knowledge and execute these complex tasks safely and reliably.
It allows the workflow owners, the people who actually know how to run a financial audit or how to train an LLM, to define their own logic and distribute it widely and portably.
Agent Skills packages up the intellectual pre-work that's required for advanced automation.
This has been an incredibly detailed look into the architecture of modern agents. The key takeaway for me is that Agent Skills really forces an engineering discipline upon agent development.
It really does.
It empowers workflow owners to compartmentalize their most complicated automation logic. And that leads to agents that are more reliable, more consistent, and significantly more token efficient through progressive disclosure.
We are witnessing a critical shift. We're moving from focusing solely on building a powerful brain, the LLM, to building a powerful structured methodology for how that brain uses tools and executes multi-step tasks in the real world. This reliance on clear, token-efficient documentation is, I think, the next great leap in making agents useful at scale.
Looking ahead, where does this standardization lead the industry? If we have this format for packaging workflows, what's the logical next step for distribution?
I predict the expansion of agent skills into what will rapidly become off-the-shelf agents. Currently, we have the skill packaging the procedure, and we have the concept of high-level instruction prompts in files like agentsS.md. In the near future, I can easily envision consulting firms or specialized software vendors packaging a set of essential skills together with a supporting agent harness configuration.
So you're creating easily distributable, specialized expertise packages. Like you could download an agent for German tax law auditing that comes preloaded with the 10 specific skills and all the domain knowledge it needs, all structured via this standard.
Exactly. This allows for the easy, standardized distribution of immense domain-specific knowledge to already capable agent harnesses. You buy or you download the expertise, not just the model or some simple API wrapper.
That brings us to our final provocative thought for you, the learner. This whole movement towards standardization, it necessitates critical thinking and clear documentation from us. When you next interact with an AI tool, whether it's a code generation tool or a summarization service, consider the underlying skill it might be running.
What complex multi-step workflow is that AI following that you never explicitly ask for? And how is it using progressive disclosure to save tokens?
And considering this architectural shift, how does this standardization affect your job or your industry today?
Right. If you work in finance, you likely won't wait for your model vendor to build a financial analysis tool. A specialized consultant might just sell you the financial auditing skill package directly. So if you were to design a skill for your own job, what is the single most complicated multi-step process you would document in skill.md to guide an agent reliably?
And ensuring you follow those best practices for the 100 token limit and the conditional clarity.
Thinking this way moves you from being just a user of AI to an active architect of AI capability.
That is a fascinating challenge. Thanks for joining us for this deep dive into the architecture of agent skills. We'll catch you next time.